You're welcome to my YouTube channel, and in this video, this is the introduction to a new series called Fourier series. And Fourier transfer, yeah, this is the Fourier series. Introduction to the new series, the Fourier series. And in the Fourier series, before you need to understand what Fourier series is all about, you need to understand the periodic function. You need to understand what a periodic function is. Now, what is a periodic function? A periodic function is any function that repeats itself over a period, that is at that same period it keeps repeating itself continuously, either discontinuously or continuously, but continuously. And an example of a periodic function is the sine function. Now, the graph of a sine function is something more like this, in such a way that it continues up to infinity, and the distance from here to here is 2 pi. This is what a sine function is. We have pi here, 2 pi. This is 3 pi. Here we have minus pi, minus 2 pi, minus 3 pi. At that same point of 0 to 2 pi, it keeps completing one oscillation. And this is a sinusoidal function. This is the graph of sine x. Also, the graph of cos x. The graph of cos x is something in this way, whereby from minus pi over 2, from minus pi over 2 up to from minus pi to pi here. From minus pi, hmm, from minus pi up to the point pi. And that is from a periodic function, whereby the entire period function is from here to here, right? The time that it takes to complete a full sinusoidal function is 2 pi, which is the period. Over this period of 2 pi, it keeps continuing, it keeps repeating itself over and over again. So this is the example of what a periodic function is like. So now let us move on a little bit. Let's move on a little bit. We have this minus pi over 2 pi over 2. Let us move on. Oh, yeah. Yeah. So now let us move on. Since now that we have an idea of a periodic function, so we need to know how we express a periodic function. Now, a periodic function, if f of t, how do you know it is a periodic function? Is when f of t is equals to f of t plus the period t, that is the full span of the entire oscillation of the entire period. In that way, this is the way that we identify a periodic function. Now, why am I mentioning periodic function? The reason why I'm mentioning periodic function is because in Fourier series, what we are trying to do is to express a function in terms of cos and sine. That is, we are trying to express a function, let's say a function x or a function 2x squared, in terms of cos and sine. And the form of expression of a periodic function is f of x is equals to a naught over 2 plus summation from 1 to infinity, when n equals to 1 to n equals to infinity, of a of n cos nx plus this the summation from of b of n sin nx. And it's something like, let's say we have a1 cos 1x, a2 cos 2x, a3 cos 3x. That is the way that it goes. It's not magic, it's not space magic. So now that is the way. Now, what is, since I have explained this, what are the main problems, like what are the main things that we need to know about Fourier series? And the main things we need to know about Fourier series is the constants. The constant a naught, a n, and b n is what we need to get. We need to get the constant because the value for n is already fixed, and we do not need to find for the value of x at all. What we need to find is the value of bn, an, and a naught. And once we get these three values, we input them into that formula there, and we have gotten our Fourier series. That is, we have just expressed it in form of Fourier series. That is what they need us to do, which is going to be the main thing that we are going to be doing in this entire series of, or in this entire playlist called the Fourier series. So before I move on to the next chapter, which is finding for the constants, I want to give you a little bit of hints that can help you in understanding Fourier series very well. Like, instead of going through a long stress of solving integrals, you can just know these useful integrals over here that is going to help you a long way. It's going to go a very long way. Instead of you doing an integral of 4 lines and finding out that it's zero, you can just put in that since the integral from 2 pi to 0 to 2 pi cos nx dx equals to 0, then this is equal to 0 in that particular manner. Or things like cos nx, which you can simply not do without, is the fact that sin nx equals to sin n pi is equals to 0, and cos n pi is equals to minus 1 raised to power n, is something that you cannot do without in the Fourier series at all. So now let us move on with our series. We need to understand the useful integrals here, which is the first one is integration from 0 to 2 pi sin nx x is equals to 0. Same thing with cos nx. Now the same thing with when we have cos sin nx sin mx, the x equals to 0. In such a way that we have sin 2x times sin 3x, when it's integrated from 0 to 2 pi, it's going to end up giving us 0. So once we see that kind of pattern, we should already know that this is going to give us 0, and input our value 0 already. The same thing goes for cos nx cos mx. It's like cos 3x cos 4x in that particular scenario. Then also for inter sine and cos, whereby we have um, sin nx cos nx, that is like sin 2x cos 2x. In that particular scenario, we are also going to have that as 0. And here, whereby we have something like sin 2x cos 5x, it is also going to be 0, despite the fact that the constants at the back of x are different. Either they are different or the same, it's going to be 0. So we done this that I've explained here does not mean that everything is going to be equal to 0. You just need to make sure that this does not confuse you, and you can actually write this down. Then also we have our integration of sin square nx from 0 to 2 pi, that is going to give us pi, and that also applies for cos square nx. So then the basic ones you need to know here, which you cannot do without at all, is the sin n pi is equal to 0, cos n pi is equal to minus 1 raised to power n. So meet me in my next video, whereby I'm going to talk about how to get our constants a naught, a n, and bn. Thank you very much.